Alright guys, welcome to this series on well test analysis by petroleum from scratch. We were discussing about the diffusivity equation. We understood the intuition behind how it looks like and what assumptions does it take, but this time we'll understand why do we need a diffusivity equation, how and what is happening inside the reservoir. So this is the well and this is the reservoir. So you have withdrawn fluid from the well, some disturbance is created, and this is the disturbance. At T1 time, as soon as the disturbance is created, before the disturbance, this is the pressure, constant throughout the reservoir, undisturbed. As soon as you withdraw fluid, the voidage creates a disturbance like this, and with time it varies and it pressure drops, keeps on dropping. So you can see that it is varying with respect to radius with this curve, something like a logarithmic plot, as well as it is varying with time like this. So the pressure is a function of radius and time. So there must be an equation that describes this phenomena. Diffusivity equation is that equation that describes this phenomena. Alright, so we're back to the diffusivity equation now. This is our reservoir and this is the reservoir thickness. This is the well and this is the reservoir element that we are considering. So suppose we are withdrawing fluid from this well. So we have taken an element. What will happen inside the element will give us the diffusivity equation. So the element is such that the inner surface is at R, the outer surface is at R plus dr, and the thickness is dr, right? So the fluid is flowing like this, right? M in, M out, and some must be accumulated. So the first equation that we'll be writing over here is the mass balance. M in minus M out equals M accumulated. So 30 kgs for example are getting inside this element, 20 kgs per second are getting outside this element. So 10 kgs is getting accumulated. Simple mass balance. So this is the first equation. Now density equals mass per unit volume, and mass gives you density into volume. Divide both by time, you get mass flow rate equals rho times of Q, right? So this is another equation. Now we'll input this equation into this, but with a convention that mass in is taking place at R plus dr, mass out is taking place at R. So mass in is equals to rho Q. This is taking place at R plus dr minus mq, it's taking place at R, and this can be written as this, right? Simple. So we have reached our second equation. Now we'll keep on going ahead. The second concept that we'll be using in this case is the definition of mass accumulation. Where is the mass getting accumulated? Within the pores of this volume, right? And the pore volume is given by the bulk volume, which is 2 pi r h of this cylinder multiplied by thickness and multiplied by porosity. This is the pore volume. I hope you agree. And density times of pore volume will give you the mass accumulated. So your equation becomes rho Q at R plus dr minus rho Q at R equals del by del T of 2 pi RH phi dr. Now everything that is of dr, we'll take it to the left hand side because left hand side is a function of R. We want our equations be like that, right? So rho Q R plus dr minus rho Q R equals upon R plus R multiplied by dr, because we are taking this to left hand side, del by del T, oh there must be a rho, so del by del T 2 pi rho H phi, right? So this is our third equation. Now this looks like y2 minus y1 upon x2 minus x1. So this is nothing but a partial differential of rho Q with respect to R, and this is constant and this is constant. We take it outside, 2 pi h del by del T rho phi. Now rho and phi can vary with time, right? So we are keeping that inside the differential. Now here we'll keep the Darcy's law, which is nothing but k times of area. Area is 2 pi r, it's the curved surface area of the cylinder, 2 pi rh ka by mu del p by del r. We'll keep it here, and here you can see it is this one is del by del T of rho phi. We'll substitute everything. Del rho 2 pi r h by mu k del p by del r. Left hand side is sorted. 2 pi. Now by the multiplication rule of differentiation, we get rho del phi by del t plus phi del rho by del t. Alright, so now this is sorted. We can simplify it by cancelling 2 pi and 2 pi. There must be an h over here as well, so it gets cancelled. So our equation becomes 1 by r by del r of rho k by mu r del p by del r, right? And this is rho del phi by del t plus phi del rho by del t. This is the simplified version, and we'll keep on solving it further. Alright, so we can see over here is that r is still in here, and it cannot be taken out because this is differential in r. Now by chain rule of differentiation, RHS can be written as rho del phi by del p multiplied by del p by del t. Similarly, the second part can be written as del rho by del p multiplied by del p by del t. Now, the fluid compressibility, fluid is of density rho, right? So the fluid compressibility can be 1 by rho by del p. Think about it. This is more like an homework assignment. You can think about it. And the rock compressibility can be written as, since rock has no compressibility, the only compressibility of the rock, or books call it the formation compressibility, it will be 1 by del phi by del p, right? So we'll put both of these things. How we'll put both of these things is, these are the terms that we'll be substituting. Okay, so this is one term, this is another term. We'll substitute both of these things into this. So RHS becomes rho times of del phi by del p, right? Rho times of phi into CF del p by del t plus rho times of phi into CR del p by del t. Alright? Right. So this is where we have come at. The LHS stays like that, and we did a bit of solving for the RHS, and it is in this form. You can see that rho phi and del p by del t can be taken out common, and what comes is rho phi. In the bracket, it will be left as CF plus CR, which can be written as CT, which is the total compressibility of the formation involving fluid in the rock, and it can be written as del p by del t, and it becomes 1 by r del by del r of rho k r by mu del p by del r, right? And this is the final form of generalized diffusivity equation. It's still not in the form of equation that I told you about, but we'll get to that. This is applied for gases, liquids, everything, right? Now we'll get to the equation that we know, and it's for slightly compressible fluids. That means for slightly compressible fluids, you can take density to be constant, and if it is assumed to be constant, we can cancel it out, and what remains is viscosity can also be assumed to be constant. Permeability is, because it's a single phase fluid, 100% saturation with one fluid, it is constant, so we take it here. So it becomes 1 by r del by del r of r del p by del r equals phi ct mu by k del p by del t. Solving this, we get by the multiplication rule of differentiation, we get 1 by r del p by del r, 1 by r del square p by del r square. Oh wait, sorry, 1 by r, we'll solve it. We'll get del p by del r into del r by del r plus r del square p by del r square, and this is nothing but 1 by eta del p by del t, where eta is k by phi mu ct. So it becomes 1 by r, this get cancelled out, del p by del r plus del square p by del r square, because r goes inside, cancels it out, equals to 1 by eta del p by del t, which is exactly the form of equation that we know. I'm running out of storage. Thanks a lot from Petroleum from Scratch. See you guys soon.